Hi, we're going to look at this example. This is example 2 from our 1.6 class notes. And so we're really at the end of chapter 1 where we've been looking at solving first order ordinary differential equations, and we've talked about several different methods. I've kind of summarized them here at the right side of the screen. So the two easiest methods, and the ones you should really recognize pretty readily, are when you have a separable equation or a linear equation. And so most of you are pretty good at those right now. Some equations might be both, so you could choose your method. Separable is usually easier. But for separable, you'd separate the variables, do the integration, get your implicit solution, and then maybe an explicit solution. For linear, we have that specific technique using the integrating factor. Our book likes to use rho. Equals e to the integral of p of x dx, and you multiply through by that, and then that forces the reverse product rule, and you can finish solving it that way. And then what we've been working on in this section are sort of other ones. So on an exam, I would definitely expect you to recognize a separable or a linear equation and solve that pretty straightforwardly without too much trouble. These other ones, on an in-class timed part of an exam, I would not expect you to recognize these other ones without a hint telling you this is an exact equation or it's a Bernoulli equation or whatever. So on a take-home part of an exam where you have more time to think about it, then yes, I would expect you to be able to do ones like this without necessarily being told what type it is. All right, so let's look at these though. This is kind of what we're looking at here. This differential equation I have here on the screen is not separable. Might think through the algebra of that, but you're not going to be able to write it with all the y terms on one side times dy, and then all the x terms on the other side times dx. It's not linear. That's pretty easily discernible by looking at the y times dy dx that's in there. It's not an exact equation, so I've written there the form of an exact equation, m dx plus n dy equals 0. And your partial derivative of n with respect to x would equal partial derivative of m with respect to y. That's how you would check to see if it's exact. So you could rearrange some terms and verify that for this one, but this is not exact. Bernoulli equation looks like the standard form of a linear equation, except you have this extra y to the n factor, power of y factor there. This is not a Bernoulli equation. Homogeneous equation can be written in the form dy dx equals just strictly function of y over x, so that any variables in the equation are all in that combination of y over x's. And we can't do that here. You can maybe think about doing that if you divide through by x or y, but you end up with some terms that involve either 1 over y or 1 over x, so that's not going to work here. All right, so we're kind of down to miscellaneous substitutions, and really for all of these substitutions, you're going to make some sort of substitution, u equals something, that will simplify the equation. For the Bernoulli equation, the substitution that helps is to use u equals y to the 1 minus n, and that forces the differential equation into a form that you can then work with. It's either going to be separable or linear. And with homogeneous, similarly, you can make a substitution u equals y over x, and that will force the differential equation, at least for our textbook, to be separable or linear. The miscellaneous substitutions are maybe a little bit harder because you have to figure out what to let u equal that is going to simplify the equation. And for this one, I arranged the terms in this one so that perhaps it might be obvious or more obvious than it otherwise would be what to let u equal. But this is something that sometimes takes some work and some ingenuity trying to figure out what to let u equal. On this one, it might be pretty obvious. You have a 2x plus 4y that shows up twice in the equation. There's also an x plus 2y, but if you can let u equal sort of a larger expression, that's going to clean up some of your coefficients and things like that. So if I let u equal 2x plus 4y, and then follow that through, being sure that I'm paying careful attention to all the variables. We should be able to go ahead and solve this differential equation. Alright, so I'm going to substitute that in place of the 2x plus 4y. I have one of those on the left side and then also on the right side if I factor out the minus sign from those last two terms. I need to also follow through what is going to happen for the dy over dx. And so there are a couple ways you can do that. In the Bernoulli and homogeneous equations, I tend to solve those for y, those substitutions for y. Or you can, in this one, you can just differentiate through by x. I am going to go ahead and solve for y just because that's how I've usually done it with the other ones we've looked at. And now I'm going to differentiate both sides of that with respect to x, remembering that u and y are both functions of x. Y is a function of x. It tells us that in the original notation. And if y is a function of x, then u is also going to be a function of x. Alright, so my derivatives here, I will have dy dx is, alright, so the derivative of 1/4 u. So derivative of 1/4 u will be 1/4 and then times du dx. This is like implicit differentiation because u is a function of x. And then derivative with respect to x of minus 1/2 x will just be minus 1/2. Okay, so let's go ahead and make the substitutions. So there are a couple different ways you can do that. I do have the 2x plus 4y in a couple places in the original equation, once right here and once right here. So I'll substitute u in for that. And then in place of the dy dx that I have right here, I'll substitute what dy dx is equal to. So you're really just directly substituting into the equation. Alright, so I'm going to go ahead and distribute through the u here. At this point, then, you should have an equation that you should be able to solve. This one, I have no x's in the equation at this point, just all u's. It is a nonlinear differential equation because I have u times du dx, but it is a separable differential equation. So I just need to do a little bit of algebra here to separate the variables, do the integration, and then back substitute at the end. You have a lot of choices about how you actually do that algebra, so as long as you're not violating the rules of algebra and you're keeping the equality true, then you can choose different ways to progress through this. I'm going to choose to multiply through by 4 to get rid of some of these fractions and start that way. Okay, at this point, I am now ready to do one more step here to separate the variables, but this is an important step to pay attention to. So when you solve separable differential equations, sometimes you end up with singular solutions, and that happens at the instant when you divide through by the dependent variable. So the next step that I'm going to do here, dividing through by 4 minus 2u, is where I would possibly introduce a singular solution. So you need to be aware of that and come back and look for that. Okay, so I made a little note over here to the side to remind myself that if that denominator is 0, that gives me the function u equals 2, which is a possible singular solution. Alright, from here I'm going to go ahead and just do the integration. When you do that integration on the left side, there's a couple different ways to handle that. You could do a substitution, maybe not a u substitution since you already used u here, but a w substitution maybe where you let w equal the denominator and then back solve to substitute in for the numerator, or you can do some long division. I'm going to go ahead and just do long division here. Okay, so on the left-hand side here, I did the long division in black off to the right. U divided by negative 2u plus 4. That's long division of polynomials. If you need to look up a little review on that, you can just Google that or find a video to help you refresh on long division of polynomials if that was not enough refreshing. Okay, let's go ahead and finish this integration here. Okay, so I went ahead and did the integration here. There's a little bit to be careful about in the second term in the integration. There's technically another substitution there, w equals the denominator, and so that's why the coefficient here is -1 instead of just 2. All right, so at that point I have an implicit solution in u. I need to make sure that I need to go back and change back to x's and y's since my original differential equation was in terms of x's and y's. But before I do that, I'm going to check what I had over here for the possible singular solution. So I want to see, is there a choice of c that would include u equals 2? You can look at the c, but the other thing to pay attention to is that I cannot plug u equals 2 into this equation. That would give me ln of 0, which is undefined. So u equals 2 is a singular solution. So I should go ahead and list that as part of my solution here. And then I need to back substitute for u, so I'm just going to put in what we originally let u equal, 2x plus 4y. Alright, so here is our general solution that is in implicit form. Really can't solve that for y. And then I also have a singular solution, u equals 2. U was 2x plus 4y. So someone asked in class the other day about how do you check that the singular solution really is a solution to the original differential equation. So this singular solution, you actually could solve this singular solution pretty easily for y. And when you do that, you can just find the appropriate derivative, plug into the differential equation, you can verify that it does indeed make the differential equation true. Alright, so these are a little trickier. It's sometimes hard to figure out what to let the u equal. If you have a long time to fiddle with it, maybe you just try different things. And just like u substitution in Calc 1, you get better at it the more of them you do. But these ones are a little bit hard. I think most of them in the homework should be pretty obvious, sort of like the one we started with here, where you see this sort of common expression that shows up in the problem in multiple places. And in the homework anyway, if you try that for your u, it should work. In general, if you're just throwing a differential equation from the wild, who knows if it will work. But that's when you just have to kind of fiddle with it and see what's going to happen. So, all right, try some homework.